Hi there, welcome to our presentation. My name is Nikolaos Mithianoudis. I'm a professor at the Department of Electrical Computer Engineering at the Democritos University of Thrace in Greece, in Xanthi. And I'd like to welcome you again to our presentation of our paper. Now I'm going to share my screen. Our paper is entitled Deep Personal Identification Using Spatiotemporal Facial Motion Amplification. It's a joint work with my student Konstantinos Gentsidis, my PhD student Theodore Pistola, and Professor Nikolaos Boulgouris from Brunel University in London. Here in our paper is first we're going to introduce you to the subject, what's the motivation behind the new biometric that we're presenting, the proposed methodology, and how we set our experiment, we evaluate the efficiency of our approach, and then we're going to conclude and present some open issues and of course the conclusions of our work. So the whole paper is on biometrics. So biometrics are usually characteristics that we extend from a human subject in order to identify him in an application. So we use traditional biometrics such as the fingerprints, the iris, or the face. Very traditional biometrics, very efficient biometrics, excellent performance in large databases, and they are used in many control access situations. Nonetheless, over the last years, we have the emergence of new biometrics, such as the palm, the vein, the ear, the gait, or EEG. So these biometrics are novel. They don't perform better than the previous ones if they're standalone, but if they are combined with the traditional biometrics, what people have observed is that they enhance the performance of the traditional biometric. That's what we do here in our paper. We present a new biometric which is going to be used in combination with existing options. So the biometric we present here is the facial blood flow, which is essentially the way the blood flows in our face. Of course, this information is not visible to the human eye, so we don't need any special equipment to do that, to identify this facial blood flow, but we need only special algorithms. So we are going to use patterns that represent facial blood flow in order to identify individuals. And in order to do so, we need a normal video camera. And we use an algorithm that detects and analyzes these micro movements that are not visible to the human eye and makes them really visible and processable. So we don't claim that this new biometric can outperform the traditional biometrics, but instead it can be used to enhance the performance of traditional biometrics. And essentially, what we want to clarify is that although we use facial area, which contains several facial key points such as nose, the nose, the mouth, the shape of the eyebrows, or the shape of the eyes, which are really biometric, we don't use these key points in our identification or in our biometric. So it's something new. Of course, it's not exactly new because we presented the proof of concept last year at the ICIP 2019. Here we come again and we revisit the biometric, and we have an improved feature selection compared to our previous offering. We have exploitation of the time evolution, which we didn't do last year. We have a better deep learning modeling setup, and of course, we have a new experiment that's more robust and shows that the facial blood flow can work in real applications and not just a proof of concept. Let's have an overview of our architecture. So first, we extract the regions of interest. So as I said earlier, we don't use the whole face. So we are interested in specific areas of the face that where the blood flow is really visible. Then we are doing pre-processing to stop some micro movements that are not useful. Then we do the amplification of the facial motion. And then this is fed to a statistical classifier. In our case, is CNN, a deep learning setup that is going to identify the subject. So this architecture is slightly different to the one presented at ICIP 2019. Since here we're doing first the region of interest extraction, then we're doing all the processing, and that's so we are only processing these areas we're interested in and not the whole face that we did in ICIP 2019, and this has significantly reduced the computational cost in our architecture. Okay, So let's go and see how we identify the regions of interest. First of all, we use a face detector just to find out where the face is in the video. Then we fit an active appearance model on the face, which is these red dots you see in the left image. So the AEM produces a set of standard point landmarks on the face. And to do that, we use the work of Bulat and Jimiropoulos from 2017. And what we do then, we use these landmarks that are fitted on the face to identify the areas of interest. So essentially, we use three regions of interest. One is the forehead area, which is up here. One is the left facial area under the left eye, and another one which is under the right eye, so the right facial area. So we define three rectangulars of different size, of course, 17 times 200 and 71 times 100 for these small rectangulars. So what we've done here in comparison with the previous offering is that we have devised more robust heuristics in order to define these areas. And by doing so, we were more confident about the positions of the correct position of these points, that we increased the size of these rectangulars compared to our previous offering in ICIP 2019. So we have larger areas, more robust detection of these regions of interest. The second part of the architecture is to do pre-processing. So one requirement for our approach to work, and generally for motion amplification, is that the subject must stay as still as possible. So during the recording, we're telling the subject to stay as still as possible. But even if they do so, it's impossible for a human to stay still, absolutely still. There might be some micro movement here. Which of course will deteriorate the result of facial amplification. In order to do so, we're doing some pre-processing. We're using the phase-based motion amplification by Freeman and Waldha, and we do micro amplification with a negative coefficient, so that it stabilizes the image instead of enhancing these movements. And again, what we do here is we process only the three regions of interest and not the entire image. So after we have done this, we move to the classical motion amplification framework that was proposed by Freeman in 2012, which had an example of showing a man and showing the blood flashing on and off his face. That was the inspiration for our work as well. So we're using this approach as well to amplify the blood flow in the face. And of course, we can select the desired frequency of the motions that we need to amplify. And because we know that this is blood circulation, we know the frequency of the blood flow, and we regulate this as well. Of course, this is applied only to three regions of interest and nowhere else. Just to give you an idea of how this looks like, you get three face frames from the facial blood flow. Again, here we saw the complete face and not the actual areas that we're interested in, just to see how it looks like. So the next step was to construct useful features from these FBF sequences. So in ICIP 2019, we thought of something really easy to do and really efficient to do. So we sort of eliminated the temporal element. How? We just averaged these phase images over a period of time. That period of time was 1 second, and essentially it was 30 frames. And we constructed a blood flow template. And this alleviates the phase variance problem, of course. And now from that phase, we used to isolate the three areas, and then we concatenate them to form a single template. So we used to form a 2D FBF template, which is something like this. So this is the area, the average template from the forehead, the left facial area, and the right facial area, which overall gives you a new template of 142 pixels times 200 pixels. And this is the template that is fed to the classifier and is going to recognize the person from this information only. So the advantages of that is that it's extremely simple, doesn't work, of course, require the visibility of the whole face, just these three areas. Now, we have a couple of disadvantages that the illumination must play an important role of this, and may not be a good standalone biometric by itself, but the main worries were that the temporal changes were not modeled efficiently because we average here. So we destroy the temporal elements essentially. And the other thing that we're really worried was that, okay, forming a single image was very efficient, but here we're concatenating three different areas. So if we feed that to the CNN, to the convolution neural network, it will start make correlations over here, over these boundaries. So it will start correlate different areas that are not connected at all. So we will reach out and have wrong conclusions. So what the obvious thing to do here was to create a temporal evolution to keep evolution instead of averaging it as the third dimension. So the problem here we had that we will have a phase variance because we don't know where the phenomenon starts and stops in its subject or during different subjects. So we had something that we needed something that was going to be phase invariant, and thus was using a phase invariant transformation along the temporal revolution. That was the solution that we proposed. And a good candidate is the DCT transform, the discrete cosine transform, which is approximately phase invariant and is real values, so we don't have complex values here, and it will do our job. The other thing is the concatenation of the three areas. So here we could do a concatenated 3D cube with a temporal element being the third dimension. So instead of doing that here, we propose that we should cut these areas and feed them separately to the CNN. So we create three different separate 3D FBF tables instead of one. One area for its region of interest. And what you get, essentially what we propose to get is you get these three cubes, one cube for the forehead, one for the left facial area, and one for the right facial area. And these three cubes are fed to a CNN. The final part of our system is the CNN that is going to do the template classification. As you'll see here, these three areas are fed separately to a CNN pipeline. This pipeline, of course, is displayed here. Is a concatenation of normal convolutional 3D layers with maximum pooling and stuff. So the only difference between the pipeline 1, 2, and 3 is that the input layer is different. The size of the input layer is different. Then the output of the three pipelines is used and is presented to a fully connected dense layer, which is going to process this and do the actual classification and present you with the output, which is going to be the identity of the person who is claiming identification. So in order to train this, we use an Adam optimizer. The categorical cross-entropy is classification problem, so we use cross-categorical cross-entropy. We use only 6 tables. We didn't require much more training. We used the real and the batch normalization, which was essentially instead of the dropout that we used last year. What's exactly new here is the description of the new dataset, the new experiment that we did. Last year we had 30 subjects, but they were all filmed on the same day. And we were really worried about that because we wanted to see whether this biometric will still hold in different days, during different days. And that's what we've done here. We managed to film fewer persons, but for a longer time, and we filmed them on 3 different days. So we have 12 subjects at 30 frames per second, larger resolution, full HD compared to last year. Each sequence has the duration of 1 second. And now we had the 2 days were used for training, and the 3rd day was used for testing the recognizer. So we had 360 sequences per subject filmed on 2 different days, and we had 60 testing sequences per subject filmed on the 3rd day. We believe that this is a more robust setup to judge the discrimination quality of this new biometric. So the results are here. So what we compare, of course, is the new system that we propose here, which is down here, the separate FBF DCT cubes plus parallel CNN, with the proposed approach in ICIP 2019, which gives an 80% and an 85% the new system. And of course, we also tested whether separating the cubes or not separating them will do any difference. And here we have the DCT 3D cube, but all the areas combined to a single 3D cube that was fed to a single CNN. So we see here that this produces a huge difference. Might be two reasons for that. Of course, the correction of the special convolutions of the DCT that now is fixed, so it gives better discrimination quality. And of course, this CNN is slightly larger, and that may be the reason why it performs better. So again, what we see is that this approach is slightly more complicated in the modeling area, but it performs better than the previous one. And of course, what's really important here that both results, the 80 and the 85%, show that the FBF can perform as a biometric during different days, which is really, really, really important. We now are more confident with this biometric because of the testing during different days. So it has some strong discriminatory capacity. So this is our work. So the new biometric now is reconfirmed with a new data set and a new method with promising results. The important thing, as I said earlier, is that now we tested it on different days. The facial landmarks are not used at all. It's just 3 areas that do not contain any facial landmarks. And of course, we can do a discrimination using these areas. So we, of course, it's a new field. We have a lot of open things to explore. Of course, use more people and verify the results with more people. Of course, this is absolutely necessary to test if this works with all skin types, of course. And what we're thinking of improving is more ways of handling the temporal element of the FBF, which we don't believe we're doing yet. That well, there are many things we can improve here. Thank you for your attention. I'd like to thank you for watching our presentation. I'll be happy to answer your questions during the actual time of the conference. I ask you to stay safe and stay healthy. Thank you for watching us. Bye-bye.